Is that lunch?
Yeah, I didn't have lunch yet. This is awesome. Yeah.
All right, so this is where I have us. Does this look right?
Yes, we had a problem like that, and it was not, and we didn't go over it.
Oh. Well, if that's the case, I might bump that later. Which problem was it?
I can't remember. I did it fine. That's not the problem that I have questions on, but I was a little confused about how to do.
Okay. Well, I'll take a look at that, and I might take yours if it's ready to hand in, and I'll also.
I had my Gen Chem 2 book from last year, or when I was in lab, and so that's why I got it.
Okay. Well, very good. Very good. So we're still talking about insoluble salts, and so in this case, yeah, we have 2 salt solutions, and we're going to mix them together. And one of the catches here is to make sure that you kind of picture we're taking 200 milliliters this, 200 milliliters this. We're putting them together, and then what's our total volume? 400 mils. Yeah. So we're going to see if a precipitate would form, and if a precipitate does form, there's a follow-up question. So I went ahead and went back to, you guys don't have this slide, but I went back to part 5 because I'm like, how would they know that it would be the silver chromate that would precipitate out? And remember in part 5, I gave you these slides, these general guidelines. The sodium, what's it, silver, what was the silver chromate and sodium nitrate. Yeah, so your possibilities are sodium nitrate and silver chromate. Sodium nitrate, just looking at this, it's going to be soluble because sodium, if that's your cation, they're generally soluble, almost all. And nitrate, they're almost all soluble too.
So for the test, will we need to know that then? Like, will you tell us explicitly, like, which?
If it takes the format of my other tests, I gave you guys an outline. There actually are some multiple choice questions, and actually kind of in the multiple choice, I do ask you kind of general questions about solubility. Now, later on, when it comes to working problems, I think this is your question, I tell you which solid would precipitate.
Yeah.
So I kind of have a little bit of both there. And then I brought in, this was the other slide, and actually chromate is what your silver chromate is going to precipitate out. So I'm just kind of showing you that these kind of guidelines actually are followed for this particular example. So I hope we're all on the same page. When you run into this on a test, I don't know if I'll blatantly ask you, but I will be looking for this. What is this? This is actually showing you the exchange reaction between the 2 salts. Okay, so we have silver nitrate and potassium chromate switching partners, and we end up with potassium nitrate, but potassium nitrate and silver chromate. Okay, okay, good. Now, notice I've gone ahead and I have the solid next to the silver chromate. So the other thing I'm going to be looking for is this, for you to run with that solid. That silver chromate is the thing in question. That silver chromate is the rest of the problem. What are we interested about silver chromate? Well, we're interested in it being basically insoluble, in equilibrium with its ionized cation and anion. Then don't forget that you have to use stoichiometry here because that's important. That's going to be your exponent of the power of the molar concentration of the silver ion. So the KSP expression I would expect to see also. You know, sometimes in chemistry problems you doodle things that you may or may not use. I don't think you can go wrong in doodling this. I'm going to write one more thing down underneath it. I'm going to write the QSP expression, which, guess what, looks like the KSP expression, except it's a snapshot. It's just an evaluation tool. So we're going to do like we've been doing before to talk about solubility. We're going to take a snapshot, get a QSP, and compare it to our KSP. Okay, and I won't ask in the form of a question, I'll just remind you that if the QSP is larger than your KSP, well, ask in the form of question. Will you get a precipitate or no precipitate?
Q is bigger than precipitate.
Yes, if Q is bigger than K, you get a precipitate. Very good. So in order to get those molar concentrations to plug into our QSP, and this is where one of the problems that we're due today kind of steers you down. So we have to come up with basically the moles of chromate and then divide by 400 mils. So the moles of chromate, we can use its volume and its molarity. So we had 200 milliliters, 200 with 4 sig figs milliliters. We have to convert that to liters first, so we put 1 liter over 1,000 milliliters. Then we go ahead and stick in the molarity, which was given in the problem, 0.350 moles per liter, 0.350 moles of K2CrO4 per 1 liter of solution. And that would leave us with moles of K2CrO4, but to get to moles of CrO4 2-, we have to do this, where we have 1 mole of CrO4 2- per 1 mole of K2CrO4. And then finally, we get moles of CrO4 2- ready to divide by your 400 milliliters. Rounding to 3 sig figs, I get 0.0700 moles of your anion, your polyatomic ion. Phew. Let's go for the moles of the silver, shall we? Moles of the silver, we take on a similar pattern. We're going to take the volume, 200.0 milliliters, convert it to liters times 1 liter over 1,000 milliliters, use the molarity, which is 0.100 moles per 1 liter, and then recognize that in silver nitrate we have 1 mole of the silver ion for every 1 mole of the silver nitrate. Round again to 3 significant figures, and I get 0.00200 moles of the silver ion. So then we're ready to take those moles and divide it by 400 milliliters to get molarity. A really common mistake is, I don't think I've done this, because sometimes I say we, but what students like to do is they just want to plug those moles right into your QSP. You can't. You gotta go by molarity. So going back to the chromate, if we take the moles we came up with as 0.0700 moles, divide it by the volume, 400.0 milliliters. That will give you moles per milliliters, but you need moles per liters. So go ahead and introduce a term, 1,000 milliliters over 1 liter, and that will get you to molarity. Round to 3 sig figs, I get 0.175 molar. Phew, so that's what we're going to plug into our QSP. And we do a similar thing. This just feels like Gen Chem 1 again. Now we do a similar thing to get the molar concentration of your silver ion. We take the moles, which was 0.0200 moles of silver. We divide by the volume, 400.0 milliliters. To get it into moles per liter, we introduce 1,000 milliliters over 1 liter, rounded to 3 sig figs. I get, my computer's kind of mad. I get 0.00500 molar. So that's the other number we put into our QSP. All right. So you know what we're going to do next. Take those molar concentrations and plug them into our QSP. Be so very careful. And if you've done this correctly, you recognize that we're going to have to square the silver ion. So it looks like this. QSP, our snapshot, is equal to 0.0500 squared times 0.175. rounded to 3 sig figs, we get 4.38 times 10 to the minus 6. And then ready to just compare our Q to our K. So how many people think a precipitate will form? He's double checking. You don't think it will? How many people? Be confident.
Yeah.
Yes, you're right. I didn't read a psych. Yeah, I was waiting for Quaid to answer.
I wrote down a -2 instead of 12, that's what threw me off.
Okay. Okay, yep. So precipitate will form. Very good. You got it. That's it, man. So that answers the first question. So I mentioned at the beginning of this lecture that get your pen ready to make some X's. We are actually going to skip the last part of this question. The last part said, basically it's to what extent will the silver cation be removed from the solution. So I'm not going to worry about that. Actually, you have your marching orders for your test, and I'm not going to ask that on the test. So Dr. Snipes and I talked about it, and we just like, if it's not going to be on the test, why pull you through it in the lecture? Okay? So, if you can find this question, I'm going to skip this entire question too, because it's another sort of extent question. Not to say that you guys are not capable of doing this, it's just that it's not on the test, and I don't want to worry about it right now, okay? And I won't come back to it. I promise. Okay, so skip this question too, which to me kind of puts us at this assignment slide. Now this assignment slide had 36 and 37, which are, I think, extent precipitation questions also. So don't worry about those. So these were assigned today, 27, 28, and 31, right? Okay.
Assigned today or due today?
Due today. They were assigned and due today, yep. Which you have till 3 p.m., so. Got it done? Okay. Yay. Okay, so to me then, that puts us here. This is a fun topic, I think. I don't know if it's kind of related to, are you familiar with fractional distillation? Which basically takes a pot of liquids that's a mixture. And what you do with fractional distillation is you have it set up to I guess it would be this way, a distillation column, okay? So you basically kind of tease out the different liquids based upon their boiling point temperatures. That's fractional distillation. It's kind of fun. So if you have something that boils at 100 C, something that boils at 150, something that boils at 200 C, basically you start it at 100 C, you let the fraction come over, you bump up the temperature to 150, you let the second fraction come over. Okay, that's fractional distillation. Fractional precipitation kind of reminds me of that.
I feel like it's going to be the reverse.
What's that?
Is it kind of like cooling it down or just like adding different things?
For the distillation or precipitation?
Precipitation.
Kind of adding different things, precipitation, yeah. And I guess you could go with a temperature approach if you knew the dependency on temperature of your things you wanted to separate. But what this does is it counts on the fact that, let's see, 2 or more ions in solution capable. Okay, so usually you add some sort of reagent to this pot, okay? And we're going to actually use a burette here in a minute. So you add this reagent, and maybe this reagent has an anion, and you have 2 cations that actually would precipitate with this reagent. But one precipitates before the other one, okay? One is less soluble, the other one's more soluble. So that's the fractional precipitation. Yeah, it's kind of fun. So as I've described it, in order for this to be a success, you basically have to have a nice kind of difference between the solubilities of these potential insoluble salts, okay? You don't want them like having the same solubility, with regard to the anion you're dripping in, if you're trying to separate cations. So here's an example where we have silver nitrate going to drip in, and we have two anions. And nitrate is the spectator. So the silver cation can form silver chromate, or it can form silver bromide. And this is one where we had just done one with silver chromate. I made a big deal of it's generally insoluble. But guess what? Silver bromide is even less soluble than silver chromate. I say that because what this next slide says is look what precipitated out first. It's totally your silver bromide. So if you look at it a few times, you'll say, you'll read it and you'll see, did the chromate ion molarity change? Mm-mm. It started out as 0.01 and it ended as 0.01. So it remained constant. But did all of the bromide ion precipitate out? Not all of it, but a lot of it. You know, it went from 0.01 to 5 times 10 to minus 8 moles per liter. Okay. So that's a fractional precipitation. So let's do a problem. I'll try not to get my cadmium and nickel mixed up. So we have a solution, and kind of like you saw a minute ago, in that solution we have cadmium and nickel 2. I think I'll go ahead and see if I make a picture of this. We got time. This is the back. All right, so we have nickel 2, AQ, and we have cadmium 2. Actually, we don't call it cadmium 2 because it's always a +2. Okay, anyway, and we're going to drip in sulfide. Don't care what the spectator cation is, but I'm sure there is one. Okay. So we're going to run through the problem, which compound is going to precipitate first, given the KSPs. I'm going to give you the KSPs. Which one's going to come out first? It's going to be your nickel 2 sulfide or your cadmium sulfide. And this says when the second one finally does kick in, precipitating, what will be the concentration of the cation left that hasn't precipitated out from the first one that was precipitating out? And we are going to do that one. All right. So the compound with the lower solubility will precipitate out first. So what I would do if I was doing this, not so surprising, is this. I would make kind of analogous equilibriums for both insoluble salts. You cannot go wrong. Underneath then, and to me, you have to show the dissociation. Of course, we're just getting, for every one part of the salt, in this case, we get one part of the cation, one part of the anion. The stoichiometry is one across the board. So it's not as critical as sometimes when it ionizes to form more than one particle. And that ends up making you have to raise your molar concentration to a power other than 1. Now, underneath, if you don't mind, I'm going to write the QSP statements, just to kind of, because I can. So, of course, the QSP for the cadmium sulfide would look just like the KSP. But I'm making the point here that we are actually going to deal with the snapshot, the reaction quotient concentration, I think. Okay.
On the test, will we be given the KSPs?
Yes.
Okay.
You'll be given the KSPs if you need them. I guess there's a type of problem where you go from molar solubility to KSP.
Okay.
Yep. So I think this, what I'm trying to say on this slide is you really need to get in the habit of writing your equilibrium of your insoluble salt. Okay. So, one approach, and I think it's a good one, is to basically take your how did I do it? To take your equilibrium constant expression and to rearrange it and solve for, I kind of call it the exact sulfide molar concentration you would need to get to in order for precipitation to occur. Okay, the minimum sulfide concentration. So I can rearrange that. And so your molar concentration of your sulfide ion is equal to your KSP divided by your cadmium ion molar concentration. KSP was given. Cadmium ion molar concentration was also given. That's that 0.020 moles per liter. I think of it as like a tipping point. At that point, when your molar concentration of your sulfide ion is 1.8 times 10 to the minus 27th, at that point, you're going to go ahead and get precipitation is going to begin. We do a similar thing with nickel 2 sulfide, rearranging its KSP statement or equation, KSP equation, solving for the sulfide ion. You get the sulfide is equal to KSP divided by the nickel 2 molar concentration. In this case, the sulfide ion concentration is equal to 3.0 times 10 minus 23rd, the KSP, divided by 0.020 moles per liter, the molar concentration of the nickel 2 ion that was in your thing you were dripping sulfide ion into. So the threshold, I think of it as like a threshold, the sweet spot of your sulfide ion needs to be at least 1.5 times 10 to the minus 19th or greater. And I was thinking about this in my office, and I would almost move those equality statements, okay? I would almost take that as kind of, it needs to be greater than or equal to, I don't know. That's how I think of it, greater than or equal to. So which one's going to precipitate first? How many people think it's the first one, cadmium sulfide, going to precipitate first?
Because it's smaller, so it would take a larger number to be greater than it, correct?
Yeah. Yep. It's got a smaller threshold, so it's going to start when our sulfide ion is only 1.8 times 10 to the minus 27th moles per liter. It's going to start precipitating. And the other one, you have to drip in more sulfide ion to get it up to that higher threshold. Yep. So that's, yep. This one is going to go first. Very good.
So CDS will go first.
Yep. Cadmium sulfide. So this is just a kind of a, to say, and like, could you do this on the test? I don't know. I guess I have to be careful of giving you one of these on the test. But the fact that the cadmium sulfide and the nickel 2 sulfide both ionize to form two particles, you could actually pick off their molar solubility from their KSPs, their relative molar solubilities. And so the fact that that the KSP for the cadmium sulfide is smaller would have done it for you. Okay. So the follow-up question says, okay, so you have your cadmium sulfide precipitating. So how much cadmium sulfide, how much cadmium ion will you have floating around in there when your nickel 2 sulfide begins precipitating? Your second one begins precipitating. So I added this from earlier in there. If you go back in your notes, we found the threshold for the nickel 2 precipitating was a sulfide ion concentration of 1.5 times 10 to the 19th moles per liter. That was from earlier. So if we go with that as the molar concentration of the sulfide ion, then we can rearrange our KSP expression, solving for the cadmium ion and using that as the sulfide ion. It looks like this. There's our KSP expression for cadmium sulfide. Solve for the cadmium molar concentration. It looks like this. Where we have now that sulfide ion molar concentration is going to be the threshold of the precipitation of the nickel 2 sulfide. So it looks like this. 3.6 times 10 to the minus 29th, that was the KSP for cadmium sulfide. 1.5 times 10 to the minus 19th moles per liter was the molar concentration of the sulfide ion when the nickel 2 begins precipitating. That means that the amount of cadmium ion you have left at that point must be 2.4 times 10 to the minus 10th moles per liter, even though it started out as 0.002, 0.02. So that's the answer to the second question. Okay. I didn't look at these ahead of time, so that sometimes goes badly, but let's see what we got. These will be due on Wednesday. Let me know. It's a long time between now and Wednesday. If you have any questions, feel free to let me know. I won't be unavailable. I just won't be here. $18.40. Okay. Which one of these can be used to separate barium and calcium? And I kind of circled the anions that would be combining with your barium and calcium. And what other hints do I have? I think you're going to have to look at them one at a time. Basically look at if there's much of a difference between the solubility of those two cations with the anion that they might be mixing it up with there. Okay? That's my hint. For the next one, we're dripping potassium iodide in solution that has lead 2 and silver. This is kind of similar to what we did just a minute ago with cadmium and the nickel. So which one will precipitate first? Yep, I think you should be able to answer all those. That's similar to, very similar to the problem we just did. Okay, and then the last one, no, there's two more. It looks like this. Looks like we have the anions waiting to potentially precipitate with lead 2 that's being dripped in. And so I would write the insoluble, I would write the equilibrium of the insoluble salts and kind of go from there. It's kind of like the last one. And this last one looks like the silver is going to potentially precipitate with the chloride or the iodide. Now in this case, notice we have different molar concentrations in the thing it's dripping into. So that's all my hints for that one. So fractional precipitation, that's all I have.
Excellent.
So very good. I'll push those out there. And I think I haven't yet, but I will push out the